Imagine walking through an unremarkable urban street, entering a nondescript door, descending a staircase, and stepping into a vast, softly lit cavern beneath the city. The air is cool, humid. The hum of LED lights is gentle. On tiered racks of lush green leaves, herbs and salad mix sway in a rhythm of ventilation. No sunlight enters. Outside, traffic roars and the skyline glows. But here, food is being grown. Underground, hidden, silent, yet powerful. This is not science fiction. It's the new frontier of agriculture, moving food production underground to meet the demands of density, climate stress, and resource limits. Today we're going deep, literally, into underground farming systems, exploring how they work, what technologies power them, why they matter, where this is heading, and how it could reshape food, cities, and sustainability. Cities are swelling, arable land is under pressure. Extreme weather events and changing climate patterns threaten traditional farms. Globally, expanding populations and urban migration mean more mouths to feed, while less farmland remains available per person. Traditional farming is facing rising costs, unpredictable weather, pest and disease pressures, and long supply chains. Controlled environment agriculture is CEA. One response: growing food year-round in indoor spaces decoupled from weather and geography. Within that, underground farming pushes the concept further, using subterranean spaces, repurposed basements, tunnels, old mines, bunkers, places with little daylight, to create fully controlled agronomic systems. This shift is more than novelty. It offers potential advantages for urban centers, using underutilized space, shortening supply chains, insulating crops from external shocks, and optimizing resource use. As research shows, underground farms can yield substantially more produce per area, use much less water, and locate production very close to consumers. To understand the technology, we'll break down how an underground farm is architected, the systems it employs, and how the growth process differs from field farming. Location and structure. Bullied. Underground farms start with a space, a former bunker, an abandoned mine, subway tunnel, basement, or purpose-built subterranean chamber. Because direct sunlight is absent or minimal, the entire light, environment, and irrigation systems must be artificial and controlled. Often the structure has advantages: stable ambient temperatures due to earth insulation, lower heat exchange with the outdoor environment, less external weather variation. But also disadvantages: access, ventilation, fire safety, humidity control, and the capital cost of excavation or retrofitting. Blind systems. Because no natural sunlight is available, or minimal, lighting becomes a critical component. LED spectra tailored to plant needs are used. For example, research shows smart purple LED lighting, combining red and blue wavelengths, can accelerate photosynthesis in leafy greens, yielding up to 50% more growth in some underground Japanese facilities. Underground farming typically uses soil-free systems: hydroponics, roots immersed or supplied with nutrient solution; aeroponics, roots misted with nutrient solution or other controlled media. These methods allow for much more efficient use of water, nutrients, and space. For example, hydroponic production in CEA systems has been shown to use 2.7 times less water than conventional production. Roots are exposed to delivered nutrients, oxygen, and recirculated water, enabling precise control of growth conditions and faster cycles. Environmental control and automation. Every factor matters: temperature, humidity, CO2 concentration, nutrient levels, pH, light, airflow. Underground farms use arrays of sensors: temperature, humidity, CO2, nutrient conductivity, pH, root zone sensors, and actuators, ventilation, heating, cooling, nutrient dosing systems, pumps, to maintain optimal growth. Recent studies on IoT, Internet of Things, and agriculture demonstrate that sensor networks, edge fog computing, cloud analytics, and automated control loops are central to advanced indoor agriculture. For instance, sensors feed real-time data to a control system which adjusts nutrient pumps, lighting, ventilation. The system may use machine learning algorithms to predict optimal conditions, detect anomalies, disease, root stress, and optimize resource use. Vertical stacking and space efficiency. Underground farms maximize space, using stacked racks or vertical layers of growth to multiply yield per square meter. Instead of a single layer of field crops, you can have multiple tiers. In CEA studies, vertical farms have achieved up to 12 times the yield per area of conventional farming under certain conditions. In underground settings, the vertical dimension may be exploited along with horizontal, depending on the structure. Energy and resource flows. While underground farms save on daylight, they must cover energy for lighting, climate control, cooling, dehumidification, ventilation, and water nutrient circulation. Some facilities integrate renewable energy, geothermal heat, waste heat from adjacent buildings, or synergy with infrastructure. For example, in Japan, an underground facility uses solar panels and geothermal energy to form a closed-loop system. Water is often recirculated and nutrient solutions reused. Some systems incorporate waste heat recovery from lights or buildings, reducing net energy cost, harvesting, sorting, and distribution. At maturity, the produce is harvested, often via conveyors robots in advanced systems. Because the urban location reduces supply chain distance, freshness improves and food miles drop. The produce can be delivered directly to nearby markets, restaurants or stores, cutting post-harvest losses and transport emissions. Latest technological innovations. Munich, here's where we go into the newest, cutting-edge technologies that are pushing underground farming ahead. These innovations are the difference between modest indoor farms and full-scale subterranean agricultural factories. Smart sensors. A foundational innovation is the expansion of IoT, networks of sensors collecting data on everything from root zone moisture, nutrient concentration, pH, ambient CO2, leaf chlorophyll fluorescence, to machine performance. For example, a 2024 survey of IoT in greenhouse farming described physical device layers, communication protocols, cloud, fog computing, and applications for monitoring, controlling, tracking, and predicting. In underground farms, this means root sensors providing data on nutrient uptake, cameras monitoring leaf growth, integrated systems predicting plant stress or disease before visible symptoms appear. Machine learning, artificial intelligence. Building on sensor networks is AI/ML, algorithms that learn from historic and real-time data to optimize conditions. For instance, machine learning can predict growth rates, identify root diseases, optimize lighting schedules, or adjust nutrient delivery. A 2024 preprint on advancements in hydroponics described ML and IoT innovations as key enablers for future farming. In underground farms, AI can also help plan crop rotations, energy scheduling, for example, lighting when grid rates are lower, forecast demand, and manage the supply chain interface. Robotics and automation. Automation is rapidly advancing. Monitor plants, prune, harvest, sort. For example, container-based vertical farms use collaborative robots, cobots, for transplanting and harvesting. A study on containerized vertical farming found that cobots guided by RGBD cameras and single demonstrations can perform these tasks without task-specific programming. In underground farms, automation reduces labor cost, speeds cycles, and enables remote operation. Real-world underground farm. To ground this in reality, here are some actual examples where underground farming is in operation and innovating now. Japan's underground farms. In Tokyo and other Japanese cities, abandoned subway tunnels, basements and factories are now indoor farms. One article on this topic described how firms like Spread Kobas and New Farm Shimizu have turned semiconductor factory-style environments into vertical underground farms. The farms use robotics to automate planting, harvesting, LED lighting designed for each crop, sensors, hydroponics, and geothermal dark solar integration. They achieve faster growth cycles and high precision, supplying city supermarkets directly. The article mentions herb farms in old parking garages, old industrial malls repurposed as mini-farms, and mention of harvest being doubled in some cases. Case study, Sustainability and Yield. A 2025 paper on underground food farms as a climate-friendly alternative, reported that underground CEA systems can achieve up to 210 kilojoules per MBTU per year in some hydroponic farms versus much lower figures in other setups. That paper also pointed out that while water use is dramatically less, e.g. 13x less, than conventional farming, energy usage is significantly higher, e.g. 82x more energy per kg in some cases. The economics are highly dependent on yield, value of crops, local market premium, scale and integration. Environmental and sustainability benefits. Why does underground farming matter from a sustainability and food security perspective? Here are key advantages. 1. Water conservation. Constant recirculating hydroponic systems use much less water than field agriculture. Studies show water demand in hydroponic production could be on average 13 plus or minus 2.7 times lower than conventional production. Land efficiency and urban proximity. Underground farms enable high productivity per footprint via vertical racks. Some research suggests up to 10 to 30 times more productivity per square meter. Because they sit inside or near cities, fresh produce is closer to consumers, reducing transport time, spoilage, and food miles. That means less refrigeration, lower emissions, and better freshness. Underground farms are protected from external weather, storms, heat waves, droughts, cold snaps, pests, and soil-borne diseases. Environment is fully controlled, enabling year-round production. This improves food security in volatile climates. Reduced chemical use and soil preservation. Soilless systems avoid many soil-related issues: erosion, degradation, salinization, pests, pathogens. This means less pesticide, herbicide use, cleaner produce, and freeing up land for other uses. High capital costs and operational energy use. The upfront investment for retrofitting underground spaces, installing lighting, HVAC, hydroponic racks, robotics, etc., is high. Maintenance, power consumption, especially lighting and cooling, can make the operative cost large. The 2025 Underground Farm paper states that while water and land savings are large, energy consumption, lighting, heating, cooling, remains a major barrier. Techno-complexity and skilled labor. Bullied. Running an underground CEA farm requires a multidisciplinary team. Agronomists, engineers, data scientists, automation specialists. Sensor networks, AI, robotics, nutrient systems must be managed. Smaller operators may struggle to afford or manage this complexity. To energy and carbon footprint trade-offs. Deflate. Although underground farms reduce transportation and water use, the high energy required for lighting and climate control can offset some benefits. In some cases, energy use per kilogram of produce is many times higher than conventional farms. Crop limitations and market economics. Currently, many underground farms focus on high-value, fast turnover, leafy greens, microgreens, herbs. Staple crops, grains, root vegetables, are far less viable underground due to space, cycle length, or structural constraints. The economics depend on the value of produce, local market willingness to pay premium and scale. Also, consumer perception, underground grown, may present marketing challenges. Invoked retrofitting tunnels or bunkers requires addressing ventilation, fire safety, structural load, water nutrient disposal, access for distribution, and possibly zoning permit issues. Without regulatory and infrastructural support, the venture may face hurdles. The future, where underground farming is headed. Now let's step into the future, taking a view of where the technology and market are going and what this means for cities, food systems, and you. Scaling up and module standardization. Unresolved. We will see more modular underground farm-in-a-box systems being developed. Pre-manufactured racks, lighting modules, sensor automation bundles that can be dropped into subterranean spaces. As modular design spreads, capital cost and time to set up will drop. The 2025 Modular Hydroponic Systems article highlights this trend. Integration with smart cities and urban planning. Killing. Urban planners will increasingly design new pods or retrofit underground spaces, parking garages, tunnels, storage spaces, as agri-hubs. These farms may supply neighborhoods directly, reducing food miles, boosting resilience, and adding value to unused space. Enhanced data, AI-driven growth, and supply chain intelligence. Furnished, better sensors, machine learning, computer vision, and predictive analytics will enable farms to fine-tune conditions, reduce waste, detect disease early, optimize yields and energy consumption. For example, multimodal data integration, camera imagery plus sensor time series, is emerging to automate plant health and resource optimization. Renewable energy coupling and circular systems. Underground farms will increasingly tie into renewable energy, geothermal, solar panels, waste heat, cogeneration. Example, using LED waste heat to warm adjacent buildings, composting plant waste on site, capturing CO2 from other building processes. These circular economy linkages will improve viability and sustainability. Global expansion and emerging markets. While many current underground vertical farms are in developed countries, Japan, US, Europe, emerging economies and urbanizing regions, including Asia, Middle East, will increasingly adopt underground farming, especially where land is scarce or climate harsh. Solutions may need to be adapted to local energy costs, infrastructure, and market conditions. Practical implications and recommendations. Conduct a detailed feasibility study. Assess space availability, underground or basement, structural ventilation constraints, access to electricity renewables, proximity to market, logistic costs, zoning, permits, and capital operating cost projections. Choose crop portfolio wisely. Start with high-value, fast-cycle crops like herbs, microgreens, salad leaves. Use market research to identify demand and price premium for local fresh produce. Secure low-cost, renewable energy. Underground farms are energy-intensive. Renewable energy or reuse of waste heat dramatically improves sustainability and economics. Microphone and optimize lighting strategy. Since no sunlight enters, lighting strategy is major cost. Use LED spectra optimized for the crop. Consider dynamic schedules, circadian cycles. Integrate AI for lighting control. Keep scalability in mind. Planning for modular expansion, replication, and future crop diversification helps long-term viability. Conclusion. A subterranean revolution. The concept of farming has moved beyond fields bathed in sunlight. Underground farming systems represent a dramatic rethinking of how and where we grow our food, shifting production beneath our cities, leveraging innovative technology, optimizing resources, and bringing farms closer to people. While the potential is vast, with water savings, land efficiency, urban resilience, and year-round production, the path is not simple. Capital cost, energy demands, technical complexity, and market viability are real constraints. But the innovations unfolding today, in IoT, AI, automation, modular design, renewable integration, are closing those gaps. For cities facing space constraints, climatic uncertainty, and rising food demand, underground farming may offer a transformative answer. Are we ready to walk the stairs down and look at the future beneath the surface? If we dig deep, the seeds of tomorrow's food system lie right below our feet.